Hi guys. So in our last video, we talked about how to decide if a bond is polar or nonpolar. Today, we're going to be looking at whole molecules and trying to decide if the molecule as a whole is polar or nonpolar. So what we really have to do is look at the shape and decide if the molecule is symmetrical or asymmetrical. So this mnemonic device, SNAP, is going to help you decide. If the molecule is symmetrical, then we can say that the molecule as a whole is a nonpolar molecule. And if the molecule is asymmetrical, then we can say that the molecule as a whole is a polar molecule. So let's look at what that means. I have an example down here, CH4, right? And this CH4 molecule has a tetrahedral shape. There are no lone pairs on the center atom pushing any of those H's closer together. They're all exactly 109.5 degrees apart. So even if you're thinking about partial charges, guys, how like the hydrogens are partially positive and the carbon is partially negative, you would think that, like, okay, these are polar bonds. The molecule as a whole is actually nonpolar because all of those H's and their positive charges, they're distributed evenly around the center atom. They're all 109.5 degrees apart, and they're all the same element. So this is a symmetrical molecule. It's nonpolar. There's no dipole that's created here as far as the whole molecule goes. There's not like a positive and a negative side to the whole molecule. It's all evenly distributed around the center. Okay? Where if I look at NH3, as far as the electron domain geometry goes, this N also has four things sticking off of it. It's in that tetrahedral domain. But because one of them is a lone pair, those hydrogens are being pushed closer together. Okay? All of these positive hydrogens are being pushed down, and this nitrogen is partially negative. There's like a positive and a negative side to this whole molecule. So this molecule as a whole is asymmetrical. The charges are unevenly spread out around the center atom. So we would say that this molecule as a whole is a polar molecule. All right. So, guys, this is just another visual or some other like wording you might see. So carbon dioxide, again, is an example of having polar bonds. C and O have very different electronegativities, right? So those bonds are polar. But because the molecule as a whole is symmetrical, its positive and negative partial charges are evenly spread out, we have a dipole moment of 0, meaning no dipole has been created. This is a nonpolar molecule. There's not a positive and a negative side. It's all spread out evenly. Where in water, because it's bent, our oxygen is negative, our hydrogens are partially positive. We've created this molecule that has a positive side and a negative side. So here we do have a dipole moment. We are polar because we're unevenly distributed. Okay, so I'm gonna have you guys answer these in your note packet, and I'll put some of them in the multiple choice to check how you're doing. Last thing we're going to talk about today is properties of a compound. So like, it's easy for us to look at what elements are in a compound and then decide based on the types of elements or their electronegativity differences if we're ionic or polar covalent or nonpolar covalent. But if you just have the substance in real life and you don't know what it's made of, but you still need to decide what type of bonding is in it, you can look at properties. Okay, so as far as like polar and nonpolar. These are covalent. But because the way the electrons shared are a little different, the properties on the outside are going to be a little different. So for an ionic compound, really like what tells them apart from everything else is that they conduct electricity, but only in the liquid or aqueous form. So like if I have salt, right, it's not going to conduct electricity as a solid. But if I melt that salt or if I dissolve it in water, now that salt is going to break up into ions. And those ions, because they're in the liquid phase, are going to be able to move. So electric current is going to be able to flow through. So that's like a property that's very unique to ionic compounds. Um, to tell them apart. High melting and boiling point. It's not easy to melt or boil salt. It's going to take a lot of energy to do that. But metals also have high melting and boiling points. So that's not a property alone that could be used to like identify an ionic compound. Another thing is that they dissolve in water. So we'll say what they're soluble. So if you want to know if something's ionic, you can throw it in water, see if it dissolves or not. Now, for polar covalent compounds, they also dissolve in water. So that won't be good for telling them apart from ionic, but they have low melting and boiling points. So that's a difference. They also, I don't like really that it says this, only acids can conduct in aqueous form. That's not really a good property to say is true all the time for polar covalent compounds. If they're nonpolar, they're very different. They have very, very low melting and boiling points. They're insoluble in water and they never conduct electricity. Okay. So again, guys, if you don't know what elements are in the compound, you can use these properties to help you decide something about the bonding. All right, here's some questions, and we'll see you tomorrow.